I'm going to be a little off on this tonight. It's tracing out electrical circuits and other stuff. And primarily it's going to be more other stuff. We did a pretty good job, I think, 2 weeks ago when we got carried away and we traced out circuits. We built a schematic off of a wiring setup. But this ought to be of some value to you. I'd like to hear if it is or not. Of course, you've got to watch the show first. Knowing that a circuit consists of a power source, 2 conductors, and a load, how many wires do you clamp an amp meter around when checking amperage in the circuit? And the correct answer, of course, is either L1 or L2. That's the way it's got to be. And by the way, this is just a primer for any of the entry-level techs or guys that are on the program tonight. This is going to be more of a, well, just like the rest of the webinars to date have been, it's more of a fundamental webinar. Just as a FYI, 1 amp of electron flow is 6.24 times 10 to the 8th power, which means we have all these zeros up here. Electrons flowing past a point in 1 second. This is sort of my effort at emphasizing how serious electron flow can be. An important point. So you saw how many electrons that was, and as a point of reference, that many electrons would approximately fill up a small thimble. And if you take a look at a small thimble, it's about the same size as a .45 caliber slug. So how would you like that going through your body? Think about it. Electrons are a real piece of something with a lot of power based on the voltage that's behind it. So it's very significant issue. Now, since we're talking about electron flow, and last week I was supposed to cover amp clamps used in the service side, but we didn't get there. We ran out of time. So I decided I was going to finish covering amp clamps, and then we'll get into chasing some circuits, which we've already done some of. But the amp clamps are made of laminated steel plates. All right, and so you have and I'm sure this is not news to most of you. Maybe it is. I don't know what level my audience is. But here's a laminated steel plate. This is one side of this amp clamp shown here. And what a laminated steel plate does is it's a very efficient way to pick up magnetism. This is one of the reasons that you only clamp around 1 wire. This is something I wanted to show. What we have here, and the reason those laminated plates are so important, is if you look down here in the lower left, here's a conductor with AC voltage flowing through it. And every time the sine wave changes, as you can see the sine wave going positive and then negative and so on, every time that sine wave changes, I have this magnetic flux or magnetic force that builds up around the conductor and then collapses. And it's tied to the sine wave. Boom, boom. And you can see that the sine wave goes positive, then negative, and then positive, and then negative. All right? So I'm getting a positive magnetic field built around the conductor, and then I get a negative magnetic field building around the conductor. What this does show you is, you notice the loop of wire up here turning between the magnets. Well, that's an electrical generator, a very simple one, and it is an AC generator because it has brushes rather than a ring. But with the sine wave that's presented here, it's only showing you one side of the sine wave. In other words, one side of the loop. The other sine wave, if this is 240 volt, would be going down this way and then back up. That's the reason you can only clamp around 1 wire. It's because 1 wire's got a positive if you're talking at 240 volt, or even you're talking 120 with L1 in neutral. One side is positive, the other side is negative. So they cancel each other out. That's the issue with only around 1 wire. All right, more about laminated plates. And yeah, I have a point to this. The point to this is more or less telling you about magnetism, because that's the basis of an ammeter. That's what an ammeter measures, is the magnetic energy around a conductor. Laminated plates conduct magnetic force more accurately. They reduce eddy currents in magnetic sensors and devices. They provide more accurate measurement or utilization of magnetism. So you can see I've got some examples here. I've got a motor stator. It's made up of laminated plates. All you guys, I'm sure that most of you have tore apart motors or dealt with motors. You've got a transformer here. That's an inductive load just like a motor. It's got laminated plates in it. And then we have a little shady pole motor over here that's also laminated plates. Laminated plates also in your ammeter jobs. You use them to conduct magnetism efficiently. Magnetic eddy currents, what are those about? Well, it's sort of an inefficiency related to utilization of magnetic force and inductive load. We use electricity to create magnetism, which then is an inductive load to turn a motor, to pull in a relay, to shut a contactor. We have all kinds of purposes using inductive loads. Anything when you take electrical energy and convert it to magnetic energy, it is an inductive load. Inductive load creates a magnetic force. That's the purpose of an inductive load. So eddy currents are not wanted. If you want to use the efficiency of the electricity to its highest level, then generally speaking, you're going to have laminated steel plates involved. And that's what I was just showing you with the images earlier. The magnetic eddy currents are similar. It's sort of interesting. They're similar to eddy currents that you might find in a water flow, or eddy currents you might find in a wind, some kind of fluid. That's why I put the rock in there. And by the way, this is the best place to toss the fly, just ahead of the rock, so it comes down in here and Mr. Trout grabs it. Sorry about that. Okay. Clamp around one conductor will measure amperage flow. Clamp around both conductors and they cancel each other out. This is just another slide explaining what I talked about earlier. I'm around one conductor here. You can see I'm pulling 39 amps. This is a little electric boiler that we have in the studio here. It's 240 volt, so the opposite leg, L2, line 2, is exactly opposite, 180 degrees. So if you clamp around both legs, like this picture here, they're going to cancel each other out. So you're actually measuring no amperage, but that doesn't mean amperage isn't flowing. Now, that's something that you always check with a voltmeter. Make sure that the circuit is not energized, even if you don't see amperage flowing. Point of safety. All right, be careful. Here's another possible misconception by a lot of people. The neutral wire is just as hot as the L1 or the L2 wire in a 110 or 120 volt circuit, just as hot. That is, if the circuit is flowing electrons, which means the circuit will be complete and energized. Light circuit, a small motor circuit, any 110, 120 volt circuit, if it's energized and the load is working, that white wire, the neutral wire, is just as hot as L1. Don't mess with it. If you ever have the mispleasure of disconnecting a neutral wire from the bus bar while the load is energized, you will find out that that thing is hot. Be careful. Neutral is an insulated conductor to ground, and it does conduct electrons. So be aware of that. I'm not sure where your heads are on this deal, but that's a significant issue if you aren't aware of it. Probes. Now, I've had a lot of students over the years, initially when they start using their volt-ohm meter, they get a little wimpy initially when they are sticking those probes into a contact to measure voltage or measure ohms or something. And I always say when you stick them good. Make sure you have a good solid contact with the conductors. You can see down here I'm checking out this 240 volt circuit and I'm getting a good solid reading. If you don't stick them good, and don't get carried away, however, but if you don't stick them good, then especially with the digital meters, you're going to get a shaky signal. Your readout will be sort of in and out, reading all over the place. So if you firm up your probe somewhat, then your signal should come through very good. And like I say at the bottom, don't overdo it, but make sure you have a good contact. Something about electron flow. Since we're talking about amperage, I thought I'd talk about all of it. Water. Water is a great analogy for electron flow. A lot of guys, gals, a lot of techs, they don't get the deal. And I understand that. It's not exactly an easy thing to get. Electricity, electron flow, so on. But the best analogy going is water, because everybody knows water. Everybody deals with water. You turn on the sink every day and you wash your face or shave your face or brush your teeth or whatever. You're flowing water. Well, electricity and water are direct. The analogy between the two is almost perfect. So if you have trouble with electron flow or understanding electron flow, then relate it to water. And I'll just go through this slide as we talk about it. A circuit is always two conductors, a power source, and a load. And of course, as many switches as you want. And I didn't put a switch in here with this analogy, but in the case of water, in the case of a water system, a switch would be a valve, off-on valve. Simple as that. But the minimum requirements of a circuit electrically is two conductors, a power source, and a load. That's our minimum, right? So here I have my power source represented by a pump. It could be a pump for water or a generator for electrical. I have my conductor. Here's one at the top, one at the bottom. Conductor could be, in the water analogy, the conductor is the pipe, the water pipe. In the electrical analogy, it's wire. It's copper wire, aluminum wire, typically copper wire anymore. Okay. Notice I have pressure up here. Just like in a water system, I would have pressure on the water system. The water system here at the ranch is set at 55 psi. Typical house voltage is 110 volts. Pressure is pressure. The pressure, as you know, it doesn't mean anything is happening. It just means you have pressure. So if you have the water faucet off, you're measuring 55 pounds of pressure here at the ranch, or if you have the light switch off, you can still have that 110 volt pressure in the circuit, but nothing's happening. You complete the circuit and apply that flow of electrons or water to a restriction, stupid water wheel here, or to a load like a light bulb or a motor. Okay. Electron flow is going through, comes out the other side, goes back down the other conductor. I still have the pressure's still there, and comes back up here to the power source, to the generator or the water pump. Now, most water systems that we're all familiar with are open systems, i.e. the water goes down, it goes through the restriction, and then it goes on the ground or down the drain or whatever. So there is no pressure on the outlet side. However, if you're in a sealed system, like a hydronic boiler or something like that, then you do have pressure on the outlet side. Pressure goes around and around. That's the best analogy I've ever seen for electricity. If you understand water flow and how it works, electrical flow is very much the same. If you're measuring the flow, it's gallons per minute for water, or electrons per second for electricity. And you might recall that huge number, 6.24 times 10 to the 18th power electrons flowing per second. That's our measurement for electricity. Okay? If I was in a hydronic system, I'd be looking at GPM, gallons per minute. Chasing out circuit is easier when you have some of these handy tools like this. I just thought I'd put that in there. Alligator probes, they're sweet. They're a great device, especially when you are doing the hopscotch method, which we'll get to here in a little bit. You can clamp this one clamp on one side of the power source, for example, and then you can chase the circuit down with the other end and just keep going until you find that voltage measurement. Okay, and if you understand what I'm saying, the voltage measurement is when you just went across an open circuit, or where you found the open circuit. So we'll talk about that in a minute. But I just thought, I love these probe clamps. They make it really handy. Just so FYI. Here's something that continuously surprises me with technicians. Smart technicians don't do this, but not so smart technicians do this often. One of my hot buttons on startup, as a technician then as a contractor, is before you throw that switch on that piece of equipment, make damn sure you know what you're supposed to see. And that's what I pointed out here. We've got an air conditioning data plate. I'm looking at RLA, and so here I am. I'm about ready to start this piece of equipment up. Whether it's after I did some service to it, a major service or maybe a minor service, whatever it is, I have the equipment off. Before I throw the switch and start this equipment up, you better know what you expect to see. In this case, the RLA, or the rated load amperage. I'm sure that some of you said running load amperage, but that's okay. It is not running load amperage, it's rated load amperage. Okay, and that goes back to AHRI, rating of the equipment, to determine where the amperage is when it's doing the job that it's supposed to do. In this case, I can see in the model number up here, this would be a 5-ton. It says 60. Model number NAC060. I'm going to assume that's a 5-ton, 60,000 BTUs a day. Right? So my compressor rated load amperage is 27.1. My fan rated full load amperage, and they don't give you rated load in this case, is 1.9. So right off the bat, before I throw that switch, I got those two numbers in my head. And of course, where am I going to have my amp meter? I'm going to have my amp meter on the common lead on the compressor. That's where I'll have my amp clamp. And when I throw the switch, what I want to see is 27 or less. The fan is not such a bother, a small motor and so on. But one thing I don't want to fry is that compressor motor. So what am I going to do if I see 31, 32? Then it's sort of a maybe, maybe not. I'm going to watch it very closely if I see more than rated load amperage. But just as a FYI, if you're starting up a condensing unit and the space that you're conditioning is warm, it's not down to temperature, more than likely you're going to see a higher than RLA amperage for momentarily until that piece of equipment starts to pull the load and starts to stabilize. They say it takes about 10 to 15 minutes for a condensing unit to stabilize from startup time. And that's pretty realistic, very realistic, right? So just FYI, where should your eyes be? Your eyes should be on that ammeter as soon as you throw the switch. Don't have your eyes anywhere else. Don't be looking across the street with that cute little person over there or anything like that. Make sure your eyes are on that ammeter because it only takes a few seconds to fry that compressor. Eyes on the ammeter, hand on the disconnect switch, know what to expect. Because this is what you don't want to see. You don't want to see the smoke. There's an image of looks like probably a condenser fan motor burning up. Looks like somebody was playing torture or something on the motor. Here's another image of a motor that's been torn down. You can see the windings here. These are nice and black. These are nice and copper. What color are they supposed to be? Yeah, what do you tell me? Lock rotor amperage, LRA. You'll notice it has that up here on this data plate. It's the same data plate we looked at earlier in the previous slide. Lock rotor on this is 144 amps, 3.7 for the fan motor. Now there is sort of a rule of thumb on lock rotor. And the typical rule of thumb, and I'm going to see if it works out here, I've got 144 amps lock rotor. I'm going to divide it by that 27.1 rated load amperage, and there you go. If you don't know, and there are a number of data plates that do not show lock rotor amperage, or the other way it might be is they might show lock rotor amperage, but they don't show rated load amperage, right? You're pretty safe, at least in my world, you're pretty safe in figuring that lock rotor amperage on a motor is going to be 5 to 6 times the rated load amperage. So if you don't have all the information, like this data plate is very nice, it gives you all the information. If you don't have all the information, you can do the math like I just did, divide RLA into lock rotor and see where it comes out. Or if you just know lock rotor, like this, 144 divided by 5, I'm going to come out pretty close, 28.8, not bad. That's less than an amp over the 27.1, but at least you'll have some kind of reference point. I hate to start things up where I don't have a reference point. The pucker factor gets extreme, especially the bigger the equipment. You fire up a 100-horse compressor, you really want to know what to expect to see on that amp meter. So we're going to try this out tonight, see how it goes. I've been flapping my jaws, and how are you guys doing out there? Is there any questions? Oh, yes, William, that is exactly right. A megger is a sweet thing. It will tell you where the motor windings are. Any questions, guys? Derek, what is the difference between FLA and RLA? FLA is full load amperage. That used to be a common number that you would see on data plates, but over the last 10 plus 15 to maybe 20 years, the manufacturers have been focusing on RLA, which is rated load amperage. And understand, rated load amperage is the amperage you should expect to see when the equipment is operating correctly and pulling the load. Yes, the high end will read inrush amperage on your amp meter. That's something I didn't mention. A lot of amp meters anymore have a peak hold lock on them. So if you're wondering what your peak amperage is, look at your amp meter. It might have a button or something on the side where you can capture that peak amperage. When checking amperage on the compressor, do you put the amp meter on the line or common? Good question. That's an excellent question. Always on the common. And the reason for that is because the common is a measurement of both the run and the start winding. Okay? If you put it on the line, as long as you're able to determine which is the run winding and which is the common, you should be able to determine that because the common wire goes to the common terminal, right? Always on the common wire to the common terminal, because that wire is measuring both the amperage going through the start winding and the run winding. And of course, the start winding shouldn't have a lot of amperage on it. It depends on the type of compressor, whether it's a PSC or not. PSC compressors will have a little bit of amperage on them all the time. If it's a capacitor start, capacitor run compressor, then generally speaking, the start winding is totally out due to the relay, either a potential or a current relay. Let's see. Was the 3.7 under LRA for the condenser fan? Now, the 3.7 was the LRA for the condenser fan. I'll back up. 3.7 was the LRA for the condenser fan. Yes, Carlos, on a single phase. That's all we're talking about tonight. Yeah, single phase common, the common wire on a single phase compressor. Absolutely. We're not talking three phase, of course. On three phase, there is no common wire. FLA, full load amperage. But you notice who asked that? Armando. Yeah, you'll notice that they don't give you FLA or full load amperage for the compressor, just for the condenser fan motor. Three-phase have to have the same amperage on all legs. That is correct. You don't have much wiggle room on three-phase. Everything should be the same. Shouldn't rated load amperage be enough? RLA? Yes, that's fine. Rated load amperage. And that's why most data plates anymore are going to give you RLA. They're not going to give you full load amperage. Okay, so we'll carry on here. Are you going to cover three-phase systems anytime soon? Carlos, you deal with rack systems. I think I like you already. That's one of my passions. We probably won't dig into three-phase until later in the year. We're doing these initial webinars. We're taking a shakedown cruise here. What I will tell you guys is that you can expect that probably within a month or two, this will be a full-time job for me. We'll be teaching online all the time. So stay tuned. It's something I've been trying to stay away from, but I think the need is there. On a normal running system, we need to check RLA anytime. Dustin, you have to understand that rated load amperage is set by the manufacturer and also confirmed by AHRI, Air Conditioning, Heating, Refrigeration Institute, that certifies the equipment to do the job that the manufacturer says it will do. AHRI tests the equipment. They have a test facility where they test every condensing unit the manufacturers put out to make sure that it does the job that it's supposed to do. So if Carrier sends AHRI a 5-ton condensing unit, AHRI is going to put it through their test facility and confirm that it does 5 tons under standard conditions, which is 95-degree ambient, 0 degrees subcooling, which is sort of weird, and 45-degree evaporator. Now that's for air conditioning equipment, right? Okay, let's talk about this schematic I got up here. I don't know if you guys are doing air conditioning, this is sort of, yeah, it could be an air conditioning system. It would be, if it was, it would be more of a commercial system, but it's very definitely a very common system in refrigeration applications. And let's just talk about how this works. I think you guys will, yeah, William, the ladder diagram, that's right. How this works, I didn't quite get finished here. I should have a ground strap on the condenser fan motor, but I don't. Sorry about that. Somebody cut the ground strap, damn it. But the gist of it is, let's talk about, supposedly I'm talking about chasing circuits tonight. All right. If you guys attended my first webinar, that I went way overboard on that deal. And we chased 7 circuits, if you remember. We had 7 loads, 7 circuits. We chased them out. And in doing so, we drew a diagram, a ladder diagram on the board. That was some good circuit chasing. How many circuits do you chase at a time? What should I hear? Come on, somebody, gimme. I want to see it. Ah! Clint, right on. Thank you. Oh man, you guys are hot. 1 circuit at a time, that's right. One issue overall, okay, Hector, uno, thank you. Eins? Any Germans out there? Eins? Yeah. Anyhow, one thing that really helps on chasing circuits or anything else that you're going to do electrically is you really need to know the sequence of operation on how this stuff works. All right, so we're just going to talk about this sequence, this setup. This could be a walk-in cooler, probably not a walk-in freezer because I don't see a defrost or anything like that. So we'll just call this a walk-in beer cooler. Convenience store city, that's where it's at. Right? So I got a 240 volt power source. I've got a motor. If you look over here at the legend, the M stands for compressor. You probably figured that out already. I've got CC switch points, and of course, what does that stand for? You guys all know, compressor contactor. And down here at the bottom circuit, I've got a compressor contactor coil. That is a load in the circuit. Okay. Got the condenser fan. I've got the CFC, the condenser fan cycler. Somebody tell me what kind of switch that is on the condenser fan cycle. What kind? Hey, come on, boys. Let's go. Yeah. No, you're wrong. Shame. Pressure. Thank you. Pressure switch. That is correct. And since you know it's a pressure switch, what kind of pressure switch? Is it close on rise or open on rise? Close on rise, correct. So it's pretty obvious. If you look at the switch, you look at it hinged here on the left-hand side, I've got my pressure diaphragm little symbol here on the bottom. If pressure goes up, then this switch is going to be pushed up and it's going to make the circuit. Okay, so it's a close on rise pressure switch. I'll ask you this one then. What kind of switch is this down here? It says stat, which equals thermostat. Well, temperature. Exactly. You guys are on it. Okay. And what kind of temperature switch? Close on rise or open on rise? Close on rise. Bam, bam, bam. So close on rise temperature switch, and then again I have a low pressure cutout that's going to close on rise, open on drop. What's it going to do? Pretty obvious. Close on rise. Yep, pressure close on rise. And if you say pressure close on rise, that means opens on drop, pretty much, right? Okay, so that's what's happening here. It's sort of funny, we, us technician people, are supposed to say what the pressure switch or the temperature switch does on rise. Don't ask me who invented that deal. But it is what it is. So we're supposed to say close on rise, open on rise, or if it's a flow switch, close on flow, open on flow, whatever. So it's sort of funny. But if you understand the schematic symbol, you can figure it out. Just look at it. Look at the hinge, see what happens when it goes up, see what happens when it goes down. All right, so I'll go through this. This is a beer cooler in a convenience store, or it could be a pop cooler, or a wine cooler, or a flower cooler. It could be all kinds of coolers. First thing that has to happen, you guys probably know this stuff, and I would assume you do, but we'll go through it anyhow. First thing that has to happen is this thermostat warms up, closes, and energizes the liquid line solenoid. Liquid line solenoid, all right? Liquid line solenoid is on the liquid line downstream with the condenser. Ideally, we would have a receiver in this system. So liquid line solenoid opens up, boom, meaning now I have refrigerant flow to the metering device, thermal expansion valve evaporator, okay? So now I have refrigerant flow to the evaporator. What's going to happen? My low pressure side is going to come up, and I'm going to go here to number 2 is the next thing that's going to happen. Number 2 is going to, pressure goes up in the evaporator because it says low pressure cutout. It's going to close on rise of pressure, so the evaporator pressure is going up. That's going to energize the compressor contactor. Of course, then what's going to happen? Next thing that's going to happen, compressor contactor is going to close these switches. There, I just closed the low pressure cutout. Compressor contactor is going to close those switches. And of course, what am I doing with my amp meter? I can verify this every step of the way by clipping through the circuits, right? If you're a sharp cookie and you know where your circuits are in the wiring box or in the panel or whatever, you can verify. I mean, you could be standing across the block with this thing happening, across the store, wherever, and you could verify each one of these steps is happening with your amp meter, right? So low pressure cutout closed, contactor coil energized, contactor coil points closed. Got a compressor running. Is the condenser fan running yet? No, it's not running yet. Okay, so head pressure came up after the compressor started. Now my condenser fan cycle are closed and my condenser fan is running. The whole thing is operating. Do any of you guys work small commercial? In that sequence of operation, in this particular case, that's right, William. Should it have a pressure or should it have a dual pressure for safety? Yeah, but whoever built this system is cheap. Carlos, that's a good comment. What would you recommend? Auto reset or a manual reset for safety cutout? Okay, Carlos, did you bail? All right. Okay, William, you work commercial. Raul, you work commercial. Scott, all right. Armando, you guys have seen this more than once. All right, well, let's see what happens and just go through the sequence operation again on the shutdown. What's going to happen first? First thing that's going to happen, and by the way, I didn't make up the slides to show you the reverse. I just sort of got lazy, so we'll just talk about it. The first thing that's going to happen is the thermostat. Okay, beer cooler's down to 31.5 degrees, and we all like cold beer. So it's down to 31.5 degrees. This thermostat is going to open, which is going to de-energize the circuit for the liquid line solenoid valve. If you happen to have your amp clamp on it, you would see it go to 0. All right. What's going to happen there? Now I'm no longer feeding any refrigerant to the evaporator. So if I'm getting no refrigerant flow to the evaporator, that means I'm sort of like sucking on a dead-end straw, right? And that's what that compressor's doing, is sucking on a dead end. So, but it continues to run, continues to pump, and what am I doing? I'm evacuating all of the refrigerant out of the low side and putting it on the high side. And of course, I can't do that all day because ultimately the pressure is going to drop on the low side, and that's what it does. It's called a pump down, automatic pump down. So low side pressure continues to drop. My low pressure cutout finally gets to the point where it opens. Boom. What does that do? De-energizes the compressor contactor coil. What does that do? Opens the compressor contactor points. System is off. Do you see a lot of freeze stats out in Montana? Yeah, you see them under every rock. Freeze stats are something that you see out here. Why do compressors pull less than RLA? Because rated load amperage is doing the whole job, right? Compressors will pull less than rated load amperage if they're doing less than rated load, or if they're doing the work that is at a lower ambient, for example, doing the work at a lower ambient. Then the compressor's doing the work, but it's not having to work so hard. Yeah, that's a good point. At 115 in the desert, your amps are always high. I was talking over for 10 degrees rise is 1 amp. Is that true? Depends on the system, Jack, but you're definitely going to see, because of the high head pressure related to 115 degree ambient, you're definitely going to see higher than normal amperage. Remember what the AHRI rating points are. 95 degree ambient, that's what, 20 degrees less than 115, okay? 45 degree evaporator, and 0 degree subcooling. I never have understood the subcooling, 0 degree subcooling deal, but that's the way they rate them. So if you are above that rating parameters, then you're going to see more than rated load amperage. Does that work? Jack, I was taught. Good. Well, I hope I helped. I've never seen a condenser fan pull full load amperage unless it burned up. Yeah, condenser fans hardly ever do that. They hardly ever pull full load. They can, but it's different. Can we talk a little about defrost timers? Ooh. Well, I'll tell you, Anthony, defrost timers are just, there's this huge spectrum, but I can put that on the list for another session. Does the coil or contactor lose power first? The coil. You de-energize the magnetic coil of the contactor, then the points open, okay? And generally speaking, those points are spring-loaded on a contactor. So as soon as that magnetic energy on the contactor coil is gone, the coil snaps open. You're welcome, Jimmy. Glad to see you. Well, I have a controls class for HVAC. Anthony, elaborate on that. We have a number of control courses. We have a full line of BAS if you really want to get into the nitty-gritty ugly stuff. Building automation systems, DDC, yada, 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 computerized controls. We have an entire program. It's always good. Yeah, check the controls of the HVAC system first to see why a system is working or not. Amanda, the first thing you notice when you walk up to the system is it running or not, right? William, where do you register? Our website, hvacredu.net. How do you get the information on the BAS? Eddy, go to our website, hvacredu.net. That's the web address, and it's on there. Variable speed drive and YAML, what is the VSD? Oh, variable speed, variable frequency? Oh, no, they're the same thing. Now I get you. They're the same thing. Well, variable speed drive could be a DC motor. So unless you're able to elaborate on that one, I'm not sure if I'm answering you right. A variable speed drive could be a DC motor. Some of the manufacturers, actually, particularly the ductless splits, like Fujitsu, I believe that they're playing with variable speed drives, and it's a DC three-phase motor compressor. Can you find sequence of operation from schematic? Yes, you can. You can find sequence of operation from the schematic, but, big but, is you have to have a fundamental understanding of the overall picture, if you will. It's not like you can walk up to a schematic and say, hey, it's going to do this, and it's going to do that, so on and so forth. You just saw me go through that little scenario with the beer cooler, or whatever cooler it was. that, just by looking at a schematic, in my opinion, it would be difficult to know what happens first. But if you have an understanding of the business, so to speak, then it's pretty easy to figure it out. Okay? Juan, you're welcome. Yes, questions are getting off topic for today. No, I didn't, Carlos. But just basically, I don't like automatic reset high-pressure controls. By the time you get there with an automatic reset high-pressure cutout, by the time you get there, whatever it's controlling is burned up. So that's just my 2 cents. All right, guys. Well, thanks for showing up. I appreciate it. I hope you got something out of this deal. There'll be another show next week, and we'll carry on with it. Okay? Have a good night.